the topic I would like to talk has been a topic that has been for a very long time an important theme, both in LPTMS and in IPhT, that at that time was called SPHT. And I will talk about spin glasses. As I say, this is and in particular on zero modes on spin glasses and on building up a theory for fluctuations on spin glasses based on these zero modes. As I say, this is a very old theme. I mean, the main actor here at IPhT was Cyrano de Dominicis. So since it is an old topic, I would like to just spend a couple of words of introductions. So spin glasses are basically paradigmatic example of a complex system, statistical physics systems in equilibrium, where you have frustration. So you have disordered interactions between spins. There is a pointer. This is the pointer, right? Oh my God. Huh? So where should I point? Oh my God. Okay. Yes, I mean, I prefer the other one. So this is complicated. In any case, I mean, one has a system with disordered interactions. So it's a simple system. So a system which is very easy to define, with spins with disordered interactions, so at the same time positive and negative. And actually, this is important because it is, as I say, a system which has paradigmatic behavior with ergodicity breaking. So if you consider, for example, the equilibrium of such a system at infinite at some temperature, you find that at low temperature, of course, I mean, I didn't specify really what is this system, because I should tell you how the J are distributed, how the different spins are connected. So you can think that everybody is connected to everybody and the J's are Gaussian. And then what you find is that indeed the equilibrium of this system is very complex with ergodicity breaking, many mutually inaccessible valleys in many different states, a complex dynamics, aging, and the phenomenon on which I would like to focus today, which is marginality. So the fact that the system has soft modes that leads to divergent susceptibilities and to fluctuations. And that this is, kind of marginality is not related to symmetry breaking, to some kind of symmetry breaking. In fact, it is related to what it is called a replica symmetry breaking. That comes from a name that comes from the method that one is using to analyze this problem. So what is the theoretical situation for spin glasses? Well, one has a fair comprehension of what happens in equilibrium within mean field theory, so models with long-range interactions. In aging, there is a very popular theory, in dynamics, there is a very popular theory of aging which gives a lot of prediction, in particular predicts weak ergodicity breaking, which is the property that no matter where you start, you lose the memory of the initial condition, which has been for a long time a dominant theory, but now it has been questioned in many systems. The one crucial aspect is what I was saying, marginality, so the fact that there are soft modes in the system, so both the equilibrium phase and the dynamical phase have marginal aspects. And this is within mean field theory. In oh my God, in finite dimension, the finite dimension, on the other hand, has resisted to 40 years of theoretical efforts to understand it. What we know is that if there is ergodicity breaking, it has to be, by symmetry reasons, of the same kind that we have in mean field. We have a theorem that tells us that there is a correspondence between equilibrium and dynamics. I will say a couple of words more later. So, for example, you can measure some quantities which are characteristic of equilibrium, which are characteristic of the fact that you have ergodicity breaking in equilibrium just by measuring dynamical susceptibilities. But on the other hand, the possibility of replica symmetry breaking, so this phenomenon of ergodicity breaking, has been much questioned within the years, and the question is not solved. So to study the problem in finite dimension, there are basically two approaches. The first one is a perturbative approach close to the upper critical dimension, which, according to the current theory, is 8 for certain aspects and 6 for some other aspects. So you can use a normalization group approach close to the upper critical dimension, or the other approach that one can use to investigate the possibility of a spin glass low temperature phase is to study the stability of low temperature phase and study the fluctuations of soft modes. And this is analogous to what it is done in usual system with continuous symmetry breaking, where you build up a field theory of interaction of soft modes, and you build up essentially a sigma model, a nonlinear sigma model. Okay, so and so this is what I would like to discuss today: how to build up the analogous of a sigma model for spin glasses based on the zero modes of the systems. Zero modes in equilibrium. So zero modes. So the physics of the system has to be, well, probably it has not been, but it has been traditionally decoded from the replica method, the method that one uses to solve the equilibrium. So the replica method consists in the following: in the for spin glasses, one needs to consider the average free energy, average over disorder. Now, averaging the logarithm of the partition function is a difficult operation. So one, instead of I detest that. So instead of averaging of averaging directly the free energy, one considers the partition function to some power n, which at the beginning of the computation is taken to be integer. Okay, then performs some analytic, cross the finger, performs some analytic continuation to real n, and continues to result to n equal to 0 at the end. So, this operation of starting from the integer moments of the partition function and then and then sending n to 0 leads to some, to some strange phenomena, and this is the reason why I call it black magic, strange phenomena in the mathematics that you use to solve the problem. So, for example, if you have typically you have numbers which are integers in the range between 1 and n that become real numbers in the interval 0, 1, and other things. Notably, the typical thing is that typically free energy is a minimum with respect to order parameters, but in spin glasses, in spin glasses, when you have n which goes to 0, minima become maxima, and so instead of minimizing with respect to some order parameters, typically what you need are the overlap within different replicas. So replicas, so if you have z to the n, you are replicating n times your system, and averaging, you introduce correlations between replicas. So the order parameter comes from the comparison between the different replicas. You need to maximize instead of maximize. So the order parameter, as I was mentioning, is the overlap between different values of the system, how much the different equilibria resemble to each other. And this is described by the famous construction by Parisi, which is the construction of replica symmetry breaking, which I will not describe. But that leads to the fact that the probability distribution between of the overlap between valleys has a continuous shape, of this kind. Now, soon after the solution by Parisi of the mean field spin glass problem, it became clear, and in particular by the contribution of Cyrano, De Dominicis, and Imre Condor, that whenever you have a function, a continuous probability function of this kind, in which you have a continuity of values of the overlap which are possible within the valleys, there should be 0 modes in the Hessian. So you consider your mean field theory, you consider the order parameter, and then you consider the small fluctuations around mean field theory, and and you find that if your function p of q is continuous in this way, there are 0 modes that are associated to each point where the function is continuous. And the origin is clear that, if you have states at all distances, barriers cannot be extensive from one state to another. So there are those 0 modes of the Hessians, which are called the 0 modes. And actually, the Dominici and Condor made a big effort to relate the existence of these 0 modes to replica symmetry breaking, and to consider those modes as kind of Goldstone bosons of replica symmetry. Now, replica symmetry is a symmetry under permutation of the n replicas at the origin, but the Dominici and Condor were arguing that this symmetry acquires the character of a continuous symmetry when n goes to 0. You see that I'm talking about some black magic, but black magic works, no? Okay. zero mode, soft modes, and marginality are not only present in equilibrium, they are also present in dynamics. In fact, the very possibility of having aging, it is because the system evolves on a manifold that tends to become more and more marginal as time passes. Okay, so at this point I would like to mention that if this kind of ergodicity breaking that one finds within mean field has to be found in a finite dimensional system, then there should be marginality, okay? And that you can see, I mean, relating some quantities between off-equilibrium dynamics that quantify the response functions and quantify violations of the response functions with respect to fluctuation dissipation theorem, to typical equilibrium quantities that describe the correlations between the dominating equilibrium values. So this allows to argue that if a spin glass phase has to exist in a finite dimension, it has to be marginal. So and now let me enter really into the topic of my talk, which are sigma models of spin glasses. So we have marginal modes, and we want to build up a sigma model that describes the fluctuations of the soft modes in space. So there have been different attempts. So first attempt that I would like to mention, I mean, this is not in order of time. In order of time, in fact, our attempt was the first. But there was a first attempt that I would like to mention by Brezen and De Dominicis at the beginning of the year 2000s, using the fact that you have an emerging symmetry that appears when n goes to 0, which is called reparameterization invariance in equilibrium. Then there is a second attempt by Gugliandro and Chamon in dynamics that realized that in dynamics you can, I mean, the dominant fluctuations are ones in which you basically can reparameterize time. I mean, I don't want to much enter into the detail, but you have scaling forms for correlation functions that depend on time, and the dominant fluctuations are such that the scaling function remains invariant, while the argument of the scaling functions can be reparameterized time. So this kind of and then there is our proposal, which is to use the overlap between coupled replicas, and I will enter into the details of that in a minute. So let me emphasize that within the replica method, one finds two families of parameters that appear in the partition functions. There are parameters which are sort of self-chosen by the system that I was mentioning. One needs to maximize with respect to those parameters within mean field theory, like, for example, the function p of q itself. So this maximization principle, it has been a mystery within replica methods for a long time, but then it has been understood rigorously by Guerra at the beginning of 2000. And there are also editable parameters which can correspond to parameters that one can fix by constraints in the partition function. And I mean, since you have constraints in the partition function is a sum of positive terms. If you constrain some parameters, obviously you get a free energy which is larger. Okay, so this is usual statistical physics. And and my proposal is that one should use editable parameters for the maximization. So what one does for the ordinary Goldstone modes? Well, suppose that you consider separate systems. Okay, if you have separate systems, you have that your order parameter can point in any direction, but as soon as you couple them, and this is the embryo of spatial coupling between different positions in space, you get that in order to have different order parameters in the two systems, you have to pay a free energy, which is which is given by the square of the difference of the order parameter. And this leads essentially, when you introduce space, to the sigma model. And in particular, I mean, you can argue that then that the cost of an interface goes like the system size to the power d minus 2, and the lower critical dimension is 2 in this system. And now you would like to do the same thing for spin glasses. And for spin glasses, I mean, the order parameter is this matrix QAB. And if you have two uncoupled systems, the matrix QAB can differ by a relative permutation, which is a strange thing. And what you expect is that when you introduce the interaction between those two subsystems, then the relative permutations become the identity. And if you don't have identical permutation, then you should pay a free energy price. But in fact, the Dominicis Condor defined infinitesimal permutations. Like, we're able to define the infinitesimal permutation, and we're able to show that if you have infinitesimal permutations, you have a free energy difference, but with a minus sign, which is good because, I mean, you need to maximize with respect to parameters. Okay? And so, I mean, you have the same phenomenon that you have orientation. On the other hand, you cannot construct a sigma model on that because, I mean, if you want to describe fluctuations, you want that the fluctuation has a positive free energy cost. Okay? Okay. And so there's this problem, and basically we said, okay, let's look at the free energy cost for having for fixing the overlap between two systems. So we consider two systems, okay, and the free energy cost to impose an overlap between two systems. And indeed, you can see that basically the spin glass transition corresponds to a transition where you pass from a situation where this free energy cost, which is this effective potential or large deviation function, has rate function, has a single minimum, to a situation in which you have a flat part in the support of the function P of Q. But this is now a constraint in the partition function, so you can use as an editable parameter to construct a sigma model. Okay, I mean, let me not enter too much in the details. So the only thing that I would like to stress is that you can build up, knowing the solution for a single replica, you can build up in a rather natural way the solution for two replicas if the overlap is in the right interval, where the potential is flat. And therefore, you have identified as this parameter P as a zero mode in the Hessian. And if you do that now the coupling. So you have a pair of systems with the same disorder, which have an overlap PA, and the pair of systems with different disorder, which have an overlap PB. You couple them, and if you want to keep a difference between the overlap between the two subsystems, the two pairs of subsystems, now what you find is that you have to pay, okay, a free energy which is positive. You exploit that to build up a spatial a model in which you have a space, and I mean, if you reason in the same way as you do in the case of systems with Goldstone modes and continuous symmetry, you say, okay, now I fix all the modes which are non-zero modes, which are massive, and I consider the fluctuation for the zero modes. I mean, if you had, and so what you can say is that, okay, I have my matrix QAB, which is parameterized as a function of this parameter P, which is the overlap. And now I variate this overlap in space, keeping the parameterization of Q fixed. And immediately what you find is that this would give a free energy which goes as a gradient of P cube. Thank you very much. Thank you very much. So gradient of P of cube is already a very interesting result. You see that what you get is a non-standard field theory where you have, which is you know, I mean, you have a cubic theory, so you have modulus of the gradient to the power cube, which is not non-standard. On the other hand, differently from the usual case of the Goldstone modes, fixing this parameter P, as we have done, does not eliminate all the zero modes in the problem. So, I mean, one remains with a lot of zero modes in the problem. So there are technical reasons of that, and therefore the idea of just considering, you know, just considering variations of this parameter in the fixed background of all the other parameters in the model is not a good one, and one should make something more. And if one, you know, optimize further with respect to the residual parameters that we identified as important, I mean, I don't enter into the technical details, one finds an even stranger result in which the kind of field theory that emerges is a field theory where the gradient is raised to a non-integer power. So we have a non-analytic field theory, and this integer power appears to be 2.5. And so what we get is a highly non-trivial field theory, which has the right, but which has the right property in the sense that fluctuations correspond to a positive free energy cost. So okay, what are the consequences of this field theory? Well, to find a consequence of this field theory, what you can do, you can consider your system, and you say, okay, what is the price if I want, for example, to have in half of the system an overlap P2, and in the other half of the system an overlap P1? Well, I mean, if you do the computation, what you find is that okay, there is a dependence on the difference between P1 and P2 to the power 5 half, but there is more importantly a dependence on the size of the system, okay, of the volume of the system, of the linear size of the system, which goes like L to the D, dimension of space, minus 5 half. Okay? So remark that, that the usual Goldstone bosons would give you D minus 2, meaning that the critical dimension is 2 for the usual case. And here we find the critical dimension, which is 2.5. So we find that the zero modes are more effective to destroy the, 2.5 in this region, in this sense, not in the sense that you have this scaling of the delta F. So meaning that the zero modes are more effective to destroy the transition. So there have been numerical simulations that tend to confirm those exponents. I mean, I don't have the time to comment them. Just want to show, I mean, trust me, those simulations confirms these exponents. This is a summary of my talk. I don't think I need to go through the summary. I thank you very much.
Thank you, Silvio. Thank you also for reminding Cyrano to us. I'm sure he would have loved to hear. He was really keen on that problem during the last years. Any questions?
Yeah. Actually, I mean, like also remembering the talk of Sylvain. In this theory, as you are speaking about replica symmetry, replica breaking. So you have a permutation of symmetry of the replica, and you need to do a sort of analytic continuation of this group for n equals 0, right? And Sylvain told us that there is a way to analytically understand this symmetry also in as a continuum limit of this parameter. Do you these issues have been used in your like for example to
what I can tell is that the characteristic of this symmetry for I mean in this strange limit of permuting zero objects seem very much to depend on the way you break the symmetry itself. Okay, so there are cases where I mean the symmetry appears to have some characteristics of a continuous symmetry, like for example this one. Okay, but here you understand that the origin of these zero modes that appear to be, I mean, to have some properties of ordinary Goldstone modes. But there are other cases, okay, where you don't have marginal stabilities within mean field theory, so where valleys are really stable valleys separated by barriers which are of order volume, where the symmetry doesn't appear to have characteristics of continuous symmetry. So I mean I think that you know, the mathematical physics of spin glasses has done a lot of progresses in understanding the things at the level of the saddle point. At the level of fluctuations, I think there is still a lot of I mean there is a lot of work to do, and there is a lot of work to do what is the nature of these zero modes at the rigorous level, and I mean and it would be very nice to have a comprehension of the method, of the replica method, of more mathematical compression of the mathematical, which at the moment is not available.
Any other question? No. In fact, I had one, but Raoul stole it from me. But maybe I can rephrase it. Do you have any description of this n going to zero limit permutation? For example, in the case of RAM, does it make sense? Or if you have just one step breaking?
Well, okay, at the level of the method, you can do the calculations, you can compute the Hessian, you can do whatever. I mean, then I know that there are, ways of, continuing permutations for n going to 0. But the problem, and consider what is the group of permutations for n equal to 0. Now, okay, in particular models, everything is clear. Clear. In the RAM, there are a lot of things which are clear. Now, but a general theory of what is the permutation group for n equal to 0 and the relation with the spin-glass theory, as far as I know, it doesn't exist. Okay.
Thank you very
Would
much.
be very nice. Would be very
Hopefully
nice.
one day.
In fact, let me add something. When the mathematicians understood the nature of the, were able to prove the Parisi solution for spin glasses, they did it with standard mathematical method. They were not able, to analyze the replica method, which would really, in my opinion, would be a mathematical breakthrough.
And they took the result and showed it.
It took the result. They took the result, and with their probabilistic method, with the,
showed it's a correct one.
they showed that it is correct one.
Indeed.
But they did not analyze the method, which is.
Thank you, Silvio. You have a question?
No.
Pardon.
Yes, I was just wanted to ask, you were talking about non-analytic field theory, and I wanted just to ask if, what is the fingerprint of non-analytic field theory? What is different?
This is a completely open point. In general, you start from the idea of Landau that the free energy as a function of order parameter admits an analytic expansion, and then you find non-analyticity, as a consequence of divergence of perturbation theory, and so on and so forth. You have the normalization group that allows you to deal with non-analyticity at the critical point. Here the situation is different. Here you have a non-analytic theory to start with. Okay, and then okay, the consequence that we have, is just at this point this interface calculation. Okay, but it would be, in my opinion, very interesting to study the theory from the point of view, for example, of the renormalization group, which has not been done.
Thank you, Silvio.